Hello everybody. In this video, we are going to continue solving another problem live from LeetCode's top interview 150 problem list. So far, we have solved all the problems up to Candy. If you haven't checked out my videos on those problems, please go to my channel and check them out. So today we are going to look at trapped rainwater or trapping rainwater rather. There you go. Okay, so trapping rainwater. Let's read the problem and make sure we understand it. Oh, this is a hard problem. Okay, so this is the second hard problem we are doing on this channel. The last one we did was candy. Yeah, that went okay, but I think I'm nervous about this one. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. I see, interesting. Well, I think I partially understood, but let's read it again. Given n non-negative integers. So we are given an array of non-negative integers. Well, they represent an elevation map. Okay, so so that's a fancy way of saying represents each value represents height of some bar. And yeah, so it's a bunch of bars with different heights. Not sure they're different color here, but okay. And then we have to compute how much water it can trap after raining. I see. So let's look at this example. So it's 0 here, 1 here, 0 here. Oh, wait. So, okay. So this color is actually water. Okay. So they are not different color. Okay. So I think I got it. So what we are given is a bunch of numbers which represent the height of different bars. So 0, 1, here 0, here 2, 1, 0, and so on. And then if it rains, then what is the amount of water, maximum water it can trap, right? And I mean, basically, if it rains more, it's going to just flow out, right? That's the problem. Okay, let's look at, okay, so in this case, it's 6. So that's 1, 2, 3, 4, 5, 6. Okay, so it says it's units of water, I guess. So yeah, okay, 6 units of water are trapped here. Okay, in this case, the the total expected out was 9. Well, they haven't given a visualization. But that's okay. I mean, we can assume that if we need, we'll come up with our own visualization for that. But we'll use this if we can. Okay. And then the constraints are, okay, so the length of, what is height dot length? Oh, wait, okay, so height is this array. Yeah, so the length of the array is between 1 and 20,000 inclusive, and the values in the arrays are between 0 and 100,000 inclusive. Okay, got it. So let's think of an approach. Well, I mean, one thing I was thinking about is if the leftmost and the rightmost bars, I actually want to call them towers. This bars is a very weird word. Anyway, so if the leftmost tower and the rightmost tower were the two biggest values in the whole array, then it's easy, right? We can just linearly scan the middle and basically we take the minimum of the left and the right. So let's say that the left was 5, right? And the right was 3. Then we take 3 because that is the maximum water that anybody within that can hold. And then we just linearly scan all the middle elements and we basically subtract from their height from 3 and we say that is the amount of water that can be held there. And we just total it up, right? So that would be a special case, but how can we reuse that approach? I mean, can we reduce a general case to that? So, I mean, one thing we could do, actually, I'm going to try to do the following. I mean, the drawing program I use is not great at, or at least I haven't found a good way. I'm going to try to create a spreadsheet and, play around with the values a little bit. It might take us a bit longer, but I think it gives us that ability to just change values and visualize. So 1 second. Okay, so what I'm going to do here is I say index and height, right? And we say 0, 1, 2, 3, 4, 5. Okay, how big is that array? Okay, 12. Okay, so 5, 6, 7, 8, 9, 10, 11, right? 0 to 11 indices. And the heights are 0, 1, 0, 2, 0, 1, 0, 2, and then it's 1, 0, 1, 3, 1, 0, right, 0, 1, 3, and then it's 2, 1, 2, 1, 2, 1, 2, 1. Okay, so let's just quickly create a column graph or a bar graph, something like that. Let's see. Insert chart. Okay, if it comes up. Okay, there you go. And yeah, I don't want a line graph. I want this. Well, oh wait. So the spacing is not good in this case. Okay, so this one is good actually. Okay, great. This is exactly what I was looking for. Okay, so now we can play around with some of the values, right? Let me make more space. Okay, so what I mean is, if so, just showing you what I was saying earlier. If this is 5 and this is 3, right? Then in that case, we can basically easily calculate everything in the middle because those are the two tallest towers in the whole array, right? And that's easy. We can linearly go through and calculate. But now let's make this a 2. I don't want it 0 just for, actually 1 second. Let me just change this back. Okay, so just make this 2. That's the only change from the original array, right? So what I'm thinking is we can basically, let's say if we take this left index 0 and right index 11, right? And we say, okay, among the two, which one is smaller? Okay, smaller is 11 index of height 1. Okay, so which means we can at least hold up to 1 unit of water in each tower based on their height in the middle, right? We may be able to hold more like in this case, but for those limits, we can actually just calculate that, right? And then we can actually divide our array into multiple subarrays, 2 subarrays, and keep doing that recursively, right? So for example, in this case, between 0 and 11, we say, okay, hey, 11 is of height 1. Let's go through each of them and see how much water we can hold if there was a tower of just height 1 on each side. And that is like these two will say 1 and 1. So we'll say 2. Okay, but that is the level we already filled up. Now let's find out the maximum in between 0 and 11. And the maximum will be this tower in this example, right? 7. So it's okay. Now, how much can 0, 7 hold on top of level 1, right? Or on top of base level, which is 1. And how much can 7, 11 hold on top of base level 1, right? And then we calculate that recursively, and then we calculate that recursively. And we keep on going until we basically have base case, right? Which is a single tower, right? And then we can't hold any water. So that would be, I mean, just extending the approach which I said, which is a special case, which is if the left and the right were the maximum 2. And yeah, our base case actually, that is the other base case, right? If the maximum we find in the middle is lower, which means, let's say in this case, if this phi wasn't a phi, and if that was just a, or 2 or so, yeah, if maximum in the middle is actually lower than our minimum of left and right, then we don't have to call recursively, because like we said, if these two are the biggest towers, then we don't need anything else. We just linearly scan. Okay, so that approach would work. I'm not sure if that's the best approach, but it is an approach we haven't really done on this channel yet, so I'm going to try to implement it. I mean, such an approach is called a divide and conquer approach, right? You basically take a bigger thing and break it up into pieces and try smaller pieces until you get a simple piece. So let's implement that. We said trap or D and Q for divide and conquer. And I'm going to use smaller variable names just to save time in this video. Okay. So what's our base case? Okay, so, well, actually, wait, sorry. This is not the recursive one. We need a recursive helper, right? So we said trap D and Q recursive int H. Well, it needs a left and a right. So let's call it L and R in the spirit of using shorter variable names for the video. That's it, right? Actually, no, we also need to pass the base level above which we are calculating for that call. So let's call it base, right? Basically, the job of each call to this function with specific values of L and R is to say, hey, given the H array, between L and R, figure out how much more we can fill on top of that base, right? That's the job. Okay, so what's the base case? Well, the base case is if the range, if L is equal to R, which means we only have one tower in the range, then we return 0, right? And in fact, we can do L is greater or equal to R, right? Because just in case we end up calling with an L value bigger than R. Actually, you know what? This can also be L plus 1. Because even if there are two towers, we can't hold any water in the middle of those because there's nothing in the middle, right? So, okay, so that's the base case. Okay, now what are we doing? So we are saying, okay, so we will say, and let's total up everything. Actually, we do need the, okay, so we say left height equals h of L and right height equals h of R. Okay, so those are our two heights. And we say min height of the two is equal to math dot min left edge and right edge. Remember we said we need to take the minimum of the two and then we can calculate what can be in the middle, right? Okay, so that's all we need, and then we write a loop, and the loop is L plus 1, right? We want to start after left and we want to stop before right, so R minus 1, right? Inclusive, yes. And then we say plus plus I. Okay, so those are all the towers for which we are going to calculate for this min height. Okay, well, we need to adjust for base, but I think the min height can still be without adjusting for base. We can adjust it here. So let's adjust the base of the ith height. So first, what is the height of the ith tower? Is h of I, right? Let's adjust by subtracting the base, because remember that much water is already filled up. Well, that could be negative, so we will make it positive, oh, sorry, 0 if it is negative by doing math.max. Okay, so that's the height of the ith tower. Now, how much can it contribute? So let's say water equals, okay, so it can contribute min height minus its own height, base adjusted height, right? Actually, no, wait. So even this has to be adjusted for base, right? So if we have already filled up that much, then minimum height, then we have to subtract that from base. And if that becomes negative, we need this as well. Okay, so we need that, right? And yeah, I think that is what we want to do. So we adjusted min height also for base, and we subtracted that from that either the base adjusted height or 0 based on whichever was bigger, right? Okay, and now that we can add to total. Yes. Okay, so this is how much water we calculated between two specific left and right indices, right? But that is only if they were the limits. Now we need to find the max in the middle. Actually, let's just modify this loop to also calculate the max, right? So let's say max equal to 0, and if it is bigger, oh wait, we also need the max index, right? Because that is how we will, well, let's start with minus 1, I guess. Yeah, I think that should be fine. And then if max is, or if like the, oh, in this case, we don't want the base adjusted height, right? We want the usual height of the ith one, and if that is bigger or equal to max, then we say max equal to, actually, is it bigger or equal to or bigger? Yeah, it just needs to be bigger, right? So 1 second, h of I, and then max index equal to I. Okay, and this just is strictly bigger. Well, actually, no, there is one, I mean, minus 1 is an invalid thing, right? So even if, actually, we should do greater or equal to that. The reason is because this 0 is a dummy 0. It's not like real 0 at a specific index. And if there was a real 0 at a specific index, then that is what we would want this to be set to. Okay, so that's that. Now that we have max and max index, there are two recursive calls we're making, right? And one is, let's say total left is a recursive call of trap D and Q recursive. H is still the same, left is L, but right is max index. Oh, what is the adjusted base though? 1 sec. Yeah, we need to figure that out. Well, so okay, so we would have filled up at least till minimum height, right? Yes, so min h should be our new base, except there is one case which is interesting, which is if the, well, actually, yeah, okay. So if the base that was filled previously was bigger, right? Well, actually, yeah, okay. So the way the code is written, that can happen, right? But I think there is a way to avoid it. So the thing I was saying is, if the base passed to us is bigger than the min h, then we should continue passing that base forward, right? So it is actually math.max of min h comma base, right? But there is one way to avoid that, and that is we basically say that, hey, the base, if min h, which is uh, if the max in the middle is actually less or equal to, so if the new max we found is less or equal to min height, then don't even call recursively, just return total. And the reason is because uh, it basically reduces to our base case we originally started this algorithm with, which means if the left and the right are the top two tallest towers, then we can stop. We don't have to call recursively, right? And in that case, the base value will never be bigger than the min h that we find if we never even call recursively like that. Okay, so that would be that. And then we say total left, total right, and in total right, we call with max index and R as left and right. And we say total R, and here we return total plus total L plus total R, right? Here, there you go. Okay, I think this works. Well, actually, there is one small change I want to make. It's very, very minor, but given that we are short circuiting, I would like to avoid that. So, I mean, we are returning in two places. That's why, right? It somehow bothers me sometimes. Okay, R is equal to 0, and if only if max is bigger than min height, then we call recursively. So here, okay, and then we already declared these variables, but we do this, we do that, and we basically ended here, and now we do this, right? So this should work. Okay, let's just go through it one more time. I think it works, but if we have some bug, right? So we are given L and R. Let's take some values. Let's say L is index 1 and R is 7 somehow. I don't know, like in just some general case, right? In that case, the min height will be 1. And then we will go through 2 to 6 indices. And for 2, the height will be the base adjusted height, but base is 0. So for 2, it will be 0 base adjusted height also. And then that can hold water 1, right? Base adjusted height and so on. And then we'll add that to here. Yeah, okay. So that should work. And this is just calculating max. So I'm not running that too much. And then I think the base adjustment is very important. I think this works, but we'll see once we run this code. Okay, so let's run this. Okay, I expected some errors we have written. Oh, just missing. Oh, wait. Yeah, I just haven't even called it here. Okay, so this is easy. We just say return trap D and Q recursive. We start with 0 and H comma length -1 as the left and right, and we don't have any base water, right? And here we say return trap D and Q of height. Okay. That hopefully is the only issue. Oh, cool. It did get accepted. That is phenomenal, actually. I was expecting some logical error somewhere. Well, we only run 2 test cases, right? So let's submit and see what happens in the entire suite of test cases. Oh, nice. It did get accepted, although it's saying we are only beating 5% in runtime. Yeah. Okay. So there is, okay. So let's figure out the time complexity. We never talked about that. And given it's like slow compared to all the submissions, right? So if we think about it, let's say, yeah, let's say that we are given an array of size 12, right? Like right here, right? So then in that case, we will run one loop here, for loop, which is of O of n. So, okay, so O of n, we have one loop. One sec, sorry about that. O of n. And then what do? We say, okay, we make two recursive calls, but one is on the subarray. Let's say they are equally divided, right? Two n by 2 calls, right? So 2 times n by 2 calls. And then each of them is going to well, I mean, two recursive calls and each of them is doing a loop of n by 2, but then each of them is also dividing further n by 4 and so on, right? So if you continue this, then this becomes O of n plus O of n and so on n times. And that becomes O of n to the power of 2, right? Okay, so that's our time complexity, and that's why it makes sense that, looks like there is a linear approach. Okay, so in fact, it turned out to be way more complicated than I initially thought. The idea started with saying, oh, if there is a special case of left and right being the tallest two towers, then we can do linearly. But in the not special case, it doesn't actually do it linearly, right? And even if we reduce to the special case, okay. Because the reason is, if we are anyway going to do it non-linearly, then there is a simpler approach, right? And that is very easy, right? Which is, okay, for any tower, we look at everything on the left, we find the maximum. And basically, for any tower to hold water, there has to be a tower taller on the left side and on the right side somewhere, right? So, for example, for tower 4 to hold water, there needs to be something bigger on between 0 and 3 and something bigger between 5 and 11. Only then 4 can hold water. So we can just find that, hey, what is the tallest tower on the left side? What is the tallest on the right side? Which one is the smaller of the two? And we subtract our height from that. That is the one. And that can be done in O of n square also, because you can find linearly the left max and the right max and so on. But given that it wouldn't improve the time complexity and hence the runtime much, right? So, but we can calculate the left max for all possible indices and store it in an array, and right max for all possible indices and store it in an array, and both of them can be done in O of n time. And then we can do the same algorithm, but this time looking up left max and right max is just O of 1 because we have pre-calculated it. So yeah, I think that would be a better approach time complexity wise. So let's try that. I mean, it uses more memory, but trap with two maxes, right? Actually, let's just do H again. Okay. So here, what we are doing is we are saying, okay, so the first thing is we want an array. Actually, let me just do the following. Final int n equal to h dot length. We have done that a couple of times when we need it like more than once, right? Left max is equal to new int of n. And then let's calculate all of that, right? So int max equal to 0, for int I equal to 0, I is less than n plus I. Okay. And okay, so when we are, okay, so yeah, what we need to do is when we are calculating the left max for the ith element, it's already the value of max, existing value of max, and then we update max, right? So what I mean is, we say left maxes of I is equal to max. We do that first, and then we say max equals math.max, max comma, h of I, not left maxes of I, right? Yeah, I think that works. And that will calculate all the left maxes, and similarly, let's calculate all the right maxes. Let's do this, and now we have to go reverse, remember that, right? So n minus 1 greater or equal to 0 minus I, and now this time, all right, right max is of I equal to that, and then the same thing here. Okay, so I think that calculates the left max and the right max. Now it's easy, right? Now we say just go through the whole array and figure out I equal to 0, how much each of the tower can hold, plus plus I, and then we just say, okay, what is the water this can hold? So it can hold into water equals, okay, so first, oh wait, so first we need the left max and the right max of that index, and we take the minimum of that. Okay, so min height equals math.min left maxes of I and right maxes of I. Okay, so we got the minimum. None of them will be negative because, yeah, because of the way we calculated, right? There will be 0 or bigger. Okay, so that's good. Okay, so that's the minimum height. Now what do? We say, hey, let's calculate the water. How much water can we hold? Well, we say min h minus our height, right? Which is h of I. Well, this could be negative, so we need to make that 0 if it is. Yes, I think we need to do that. So let's say math.max 0 comma that, right? Okay, and now we just say total plus equal to water, right? That's how much water can we have, and we say return total. Okay, I think that is all. I mean, this is way easier to prove correctness of than our previous approach. Okay, so let's run this, see what happens. Probably some compilers as usual, yeah. When I write so much code without IDE, it's really hard. Okay, cool. So that was only one compiler. That's good. Let's try to submit this. Definitely time-wise, I'm expecting better, and memory-wise, I'm expecting worse. Well, we didn't. Okay, so we did go much better in time, from 5% to 70%, but memory is about, okay, I mean, that's fine, right? A lot of implementations which are submitted probably use extra memory, and that's good. Well, I mean, I wonder one last thing to do is whether it is worth thinking about whether there is a way to avoid the memory usage, right? And remember, in the problem that we did, product except self in an array, there was a trick, right? Where well, first we did with extra memory, and then we basically had a trick where we could actually reuse the memory that we would allocate for storing the output to return to the caller. Yeah, but in that case, I think the return value was an array, right, from the function, so we could use that. And in this case, well, actually, let's at least take a look and see. So if we are calculating, let's say for any one in the middle, let's just take a regular index 4, right, somewhere in the middle, so that's not an edge case. Left max, yeah, would be 3 or 0, right max would be 7. Yeah, there's no way to kind of avoid storing them, I guess. What if we started with left and right pointers, like we did on our first approach, and then can we combine the two approaches? So let's say we start with left and right. Actually, let's say somehow we ended up on index 4 on the left and index 10 on the right. So let's say somehow our left and right, I mean, we are doing some incrementing, decrementing of left and right, but left is equal to 4, right is equal to 10. Among them, 4 is smaller, right? And yeah, so 4 is smaller. So one edge of 4 on the other side is 10, but it could have a bigger edge, and which there is, right? 7 is actually a bigger edge, index 7, I mean. So that doesn't help. Well, oh, actually, wait. So, okay, so this works, right? So even though there is a bigger tower here on the right side, this tower, the tower at 10, is, we don't need the bigger. And the reason is because we wouldn't have come to 4. Okay, so here is our algorithm. But let me finish my thought. So we basically say, okay, hey, anything before 4 should be smaller or equal to the height of 10. And if that is the case, all we need is left max while we are going from left to right, or going, yeah, and keep track of left max and subtract our height from that if we are the smaller tower between 4 and 10, right? Okay, I didn't explain that very well. So let me try one more time. So here's the approach, right? We start with a left pointer and a right pointer, or left index and a right index, which are at the beginning and the end of the array. We take the smaller of the two towers. And the reason we do that, actually it will be evident why we do that in a minute. And we calculate how much water can be trapped by that tower or at that index first, right? And then we increment that. So let's say uh, in this case, the smaller of the two is actually the last index. So we'll calculate how much water can be trapped here. And how do we calculate? We say, hey, what is the right max for that? The approach is the same. We need a left max and a right max, but now we don't need an array. We say, okay, what is the right max for 11? Oh, it's 0. What is the left max for 11? Well, the left max so far is still 0 because we haven't even moved the left pointer, right? But that is okay because the right max is 0. So by that itself, we know this cannot hold any water because we always take smaller of the two limits anyway, right? So we move the right pointer here to 10, right? Let's make this 1 to move to, okay, so now we are at right is at 10, this is at 0, so 0 and 10. So which one is smaller? Well, 0 is smaller, so we say okay, and we would have updated our right max by the value of this, which is 1, right? So okay, so now the right max is 1 and the left max is still 0. Now we look at the 0th index value, which is 1, this is 2, so this is smaller, so we say okay, let's compute how much water this can hold. Well, what is the left max for this? 0. What is the right max for that? 1. Well, what is the smaller of the two? 0. And that makes sense, right? This one, no matter what is bigger tower on this side, it doesn't matter because the tower on that side is smaller. So we increment that, we say we cannot hold any water, and so on and so forth, right? So that's the approach that actually allows us to just avoid this memory usage completely and do the same algorithm that is here, right, of left max, right max, but we don't need the left max of all the elements if we traverse in this order. Right now, the problem is we are going from left to right and right, but if we go left or right based on which one is smaller, then we don't need that extra memory. So let's try to implement that approach. Yeah, the video has become too long, but I think this is a very interesting problem. Okay, so trap, and let me just call it fast now, it's just to go a little bit quicker. Okay, so what's the approach? Well, the approach is we have a left pointer and we have a right pointer, h dot length -1. Actually, let's just do this. If h dot length is less or equal to 2, return 0, right? Just to make sure there are at least 2 elements. Probably it works even without that check, but just because I'm going a bit fast, I'm not going to bother checking for now. Okay, we will total up in our total. And then what are we doing? We're saying while left is less than right or less or equal to. I will have to come back to that, or, like less or equal to will probably work. Less could also work, but let me go a little bit faster. Okay, so what are we doing? We're saying, hey, which one is the smaller of the two, right? So let's say int left height equals h of left and right height equal to h of right. Okay, okay, so those are the heights. Which one is smaller? So we also need to keep track of left max and right max, remember? So we say left max equal to 0, right max equal to 0. Okay, and we say okay, if left height is less than right height, equal to can go anywhere, doesn't matter, then we say okay, what do? We first calculate how much water it can hold, right? So int water equals left max minus left height, right? Because left max should be always smaller than the right height. So okay, so when left is smaller than right, the one edge on the right side is right height, and we need the edge on the left side to calculate, but left side edge has to be smaller than the right side edge because otherwise we wouldn't have moved forward on the left side. So we don't have to do math.min here. Basically what I'm thinking is, do we need this, right? Do we need this? And this would work as well, but I think it's redundant, right? Because of the way we are incrementing and decrementing left and right. Okay, so we do just left max minus that. And okay, so we do need if that becomes 0, right? So math.max 0, comma that. I mean, if that becomes negative, we want to make it 0. and we say total plus equals water, and we increment left pointer. Actually, we also have to change our left max, right? So let's say left max equals math dot max left max comma left height. That's that. And then similarly in else, we pretty much do the same thing except the mirror image, right? So 1 second. Okay, so here we say water is right max minus right edge, right? Yes, same thing, right max minus right edge. Okay, and total is plus equal to water, and now we update right max. Right max is equal to, let me just, right edge. Okay, and we do minus minus right. Is that all? Is there anything else we need to do? 1 second. We have updated left. In one case, we have decremented right. In the other case, am I taking care of all the negatives? Yeah, I think so. Okay. I think this is what works, but let me just run it. Yeah, it's become too long, so instead of manually running in my head, I'm just going to run the test cases and see what happens. And hopefully this time we don't have compile errors. Oh, cool. It did get accepted. That is very good. Okay, let's submit this. I mean, we are hoping to see better memory usage and maybe similar time, right? Like, sorry about this. Oh, wow. How did we go down in a memory percentile? That is crazy to me. Maybe the memory overhead of their wrapper code or something, which I'm not sure why that would be, but because this approach is definitely better, right? We have O of one memory usage and we still have O of n time. So I think the time didn't change, which makes sense. Okay, cool. I think that is good. Hopefully this was very instructive. It was, I didn't expect to do 3 approaches, but somehow I think the first one could have been avoided with a little bit more thinking. But anyway, hopefully it was helpful to you guys. If you're liking what I'm doing on this channel, please consider subscribing to the channel and hit that thumbs up button on the video. See you guys next time.